Good morning, everyone, and welcome to this morning's E3SM All Hands webinar. Thank you for coming. I am excited to have the honor this morning of introducing Dr. Geeta Persad, who is an assistant professor at the University of Texas at Austin. Geeta also, Geeta's research focuses primarily on numerical modeling in Earth system models of the impacts of climate and weather and weather risks on society. And her group develops really innovative methods to do that. And today, and in particular, they've done a lot of work focusing on the impacts of aerosol particles on climate in ways that impact society through extreme weather risk. And so today she's going to be giving us an overview of some of the recent work from her group in that area. So thank you very much for coming again. And I'd like to, thank Geeta for joining us and hand it over to her.
Great. Thank you for that introduction, Susanna, and thanks for the invitation to talk today. I'm looking forward to sharing some work that we've been doing, really thinking about how the outcome of the Earth system modeling efforts that many of us have been working on get translated into decisions around adaptation, around management of extreme weather and other environmental risks. And today I'm going to be focusing on the work that we've been doing, thinking about the nexus of clean air policy with those extreme weather risks through the lens of these anthropogenic aerosols, these particle air pollutants that are emitted by many industrial processes in societal systems. So I think it will hopefully be familiar to many people on this meeting that aerosols have the capacity to impact weather systems, weather statistics at global, regional, and local scales. Many of you have likely seen a graph like the one on the left here that shows the time evolution of global mean temperatures under sort of all influences in black, and then the relative contributions of aerosol changes from human activities in blue versus greenhouse gas changes in red. And this is really just capturing the statistics that has emerged that aerosols have actually counteracted about 30 to 50% of the global mean warming from greenhouse gases over the industrial era. But we also know that they have a strong influence at the regional scale and on other metrics like precipitation. So, for example, a lot of work has been done demonstrating that for really complex and delicate and societally important systems like the South Asian monsoon, anthropogenic aerosols can have actually been a driving influence, for example, in declines in South Asian monsoon precipitation that have been detected over the last several decades, which is what's being shown in this graph. So we know that the aerosols can actually dominate some of these very societally relevant statistics at the regional level. And even at the local level, aerosols can actually play a very large role in weather risk. This is just showing an example from a simulation of a severe convective storm system in the Houston area, showing that same storm system simulated with and without the localized air pollution, aerosol pollution. And this figure is just showing that the radar reflectivity or overall sort of like convective severity of that storm was actually increased by the presence of air pollution. So we know that these aerosols can have strong impacts at global, regional, local scales on weather risks. And so it's particularly important that we recognize that how these aerosol emissions are going to change in the near future is actually a major source of uncertainty. So these graphs are showing the evolution of black carbon and sulfur dioxide aerosols, two of the major anthropogenic aerosol components, over the industrial era in dark brown. And then the different colored lines are showing the range of potential future scenarios of what global emissions of these pollutants might look like. And what you'll see is by 2050, the range of uncertainty in what the emissions of these pollutants may be is as large or of a similar order of magnitude to the entire growth that we've seen over the industrial era. And so given the impact that prior growth in emissions has had on global weather patterns, on regional weather patterns that have important societal implications, understanding the role of this uncertainty and what sort of risks society is going to be exposed to over the next several decades is very important. And so, myself and several other colleagues published a series of papers over the last couple years, really trying to draw attention to the importance of understanding this aerosol component in the way that we're thinking about risk assessments around extreme weather and other changes in the statistics of the Earth system. And so, we published this call to action in Nature and an associated review paper in Environmental Research Climate. And the argument that we make in these papers and that I hope to convince you of today is, as we've seen, aerosols have been a major driver of these past changes in weather statistics, and they're also a major uncertainty in near-term forcing. So there have been a number of papers recently that have been making the case that the uncertainty in the aerosol emissions over the next 20 to 30 years is actually a bigger driver of uncertainty in what sort of risks society will be exposed to than is the uncertainty in greenhouse gas emissions. Um, but we know that the aerosols have a fundamentally different impact on climate change, on the different hazards and the ways that those influence risk than greenhouse gases do. And so we likely need to be thinking about the effect of aerosols differently. But the way that our climate risk assessment frameworks are built right now is very much focused on a sort of greenhouse gas driven warming framework. And what I'll make the argument for today is that these risk assessment frameworks are currently neglecting a lot of the effect of these regional aerosol emissions changes, and that this is a real gap in how we're thinking about the risks of extreme weather going forward. So these issues are particularly important because of the ways that aerosols tend to be co-located with highly populated regions and also regions of high vulnerability. So this is just depicting this in one of many ways, showing the recent distribution of aerosol optical depth or sort of atmospheric loading of these aerosol particles overlaid with areas of really high population density, which is what I'm showing in the green hatching here. And this is just to point out that where are located is also where people are located and particularly vulnerable populations are located. And so, one of the concerns when we think about risk is the exposure of people, the exposure of infrastructure, and also the capability of those people and infrastructure to adapt or to be resilient to those impacts. And so, to the extent that aerosols' impact on weather patterns is co-located with where the aerosols themselves are, we might expect aerosols' influence on these risks to be disproportionately co-located with where people and infrastructure are located. However, we also know that aerosol emissions are not only a challenge for weather patterns in the place where the aerosols themselves are located. There have been a range of studies over the last decade or two that have demonstrated these sort of teleconnected effects of aerosols. And I'll just give one brief example. There's been studies demonstrating that the increase in aerosol emissions in Europe was a big contributor to the drought that the Sahel region of Africa experienced in the 1980s that led to famine and hundreds of thousands of deaths. So this is really highlighting the fact that these aerosol emissions are both a challenge for places that have sort of a high exposure, high population and infrastructure exposure, but they also decisions that are made about aerosol emissions in one place can have large impacts in other places. So, given the impact that these aerosol emissions have had historically, and that they are the uncertainty that they create for what might happen going forward, we would hope that we would be accounting for these effects in the way that we're thinking about the risks from extreme weather. And unfortunately, as I'm going to demonstrate for you today, there are a lot of ways in which the standard framework for doing climate risk assessment really fails to capture these effects. So if we think about the process of going from the sort of Earth system model climate projections that many of us work with to the actual process of thinking about climate risk, vulnerability, exposure hazards, making adaptation decisions based on that, making investment decisions, infrastructure decisions based on that. There's a lot of steps between the process of producing those climate projections and making decisions based on them. And so we might think about different pathways through which this happens. So in many cases, uh, Earth system model output is not being directly used in a sort of decision making or adaptive framework. If you're thinking at a local level, say I'm a water manager for a local water agency, I might take the climate projections from an Earth system model and use data that's instead been run through a regional climate model or some sort of a statistical algorithm that brings those climate projections down to a spatial resolution or a temporal resolution that I need for assessing my water supply locally. If I'm instead maybe thinking at a larger scale about issues like sort of societal damages, I might take climate projections and run them through something like an emulator or a simple climate model to let me assess a broader range, say, of policy scenarios and associated changes in weather statistics. So in both of those cases, we're taking the climate projection data and we're sort of translating it through these tools. And then in both of those cases, there's an additional step between sort of taking the Earth system data and turning it into sort of risk assessment data. And that might include running it through an impact model, a damage function, a social cost calculation, or something that produces an actual input to our climate risk assessment. So in the example, say, of the local water manager, they might take these statistically or dynamically downscaled projections of precipitation and run it through their local water system model to be able to say something about increases in demand or decreases in supply they might see going forward. Or someone interested in societal damages might take the output of a simple climate model or an emulator and run it through some sort of damage function that they might have for something like crop yields or economic productivity or something like that. And what I'll show through a series of examples today is that many of these steps have assumptions built into them that obscure the effect of regional aerosols in driving climate risk. So at this first step, this translation of the climate model of the Earth system model projections, many regional climate models or the statistical downscaling algorithms omit aerosol processes altogether. And many of the emulators or simple climate models that are used to translate climate projections at a more global scale also do simplifications. They'll often use either scalings by things like global mean temperature or global mean radiative forcing, or they'll scale spatial patterns based on greenhouse gas-driven climate change in order to simplify the projected changes in statistics. And both of those choices obscure the ways in which regional aerosol emissions create these unique patterns and unique pathways of influence on extreme weather statistics. And then at the impact model stage, there are a lot of choices that go into designing impact models, designing damage functions that rely on assumptions about the pathways through which impacts can happen. And so many of these models are often built around greenhouse gas-driven damages that in some cases may end up neglecting the pathways through which aerosols could influence those same societal outcomes. And so the result of all of these together is that many near-term climate risk assessments tend to exclude aerosol effects or to sort of simplify them as a global mean offset to greenhouse gas-driven warming, which is going to lead to a lot of potential blind spots in how we're thinking about climate risk. So I want to show just a few examples illustrating these sort of different gaps in the way that we're thinking about climate risk with respect to aerosols. So focusing first on the fact that these regional climate models tend to emit aerosol processes. This is just an example from the European Eurocortex initiative, which is a regional climate modeling initiative that's used for planning and adaptation measures across Europe. And what I'm showing you here are summertime temperatures projected over the next couple decades. In orange is from the sort of parent Earth system models that drive the regional climate models. And in green is the outputs as predicted by the regional climate models themselves. Now, none of these regional climate models include the time evolution of aerosol emissions within the regional climate model domain. And what we're seeing here is, and this has been reinforced by a number of other papers since ours, is that the regional climate models systematically underestimate warming over this region because they fail to capture the reduction in aerosol emissions and resulting reduction in the cooling effects of aerosols over this region going into the future. And so in contrast, on the right-hand side, I'm showing a pairing of a parent Earth system model with a regional climate model that does include interactive aerosols, and you can see that that offset disappears. And so the outcome of this study and many others that have been done have indicated that, for example, the estimates of European warming from regional climate models that do not include aerosol changes are often off by about 1.5 to 2 degrees Celsius. So if I am a planner trying to adapt or manage or invest in ways of mitigating the impacts of heat extremes going forward, and I'm estimating based on a world that's 1.5 to 2 degrees cooler than what the reality is because I'm neglecting aerosols, I'm likely to make some misinvestments. A second example is in this context of these sort of this global average or scaling based on sort of global mean temperature. This is also has a lot of problems when we think about aerosol impacts on climate risk. So I'll use an example here from some work we've been doing on aerosols influence on heat wave hazard and exposure that really shows that the spatial pattern of aerosols influence on this particular form of climate risk and also the way it evolves through time is very unique compared to greenhouse gases. So on the left-hand side, I'm showing you the change in heat wave frequency between a historical baseline and sort of the near the next 30 years from an all forcing from an all forcing large ensemble. So this is with all sort of anthropogenic influences, and as you might expect, heat wave frequency, so the number of days per year with where a heat wave is occurring increases over all land areas, and particularly over regions with high population density, which is what I'm showing in the black stippling. On the right-hand side, though, is the aerosol component of that all-force change that I'm showing on the left. And you can see that the aerosol spatial pattern is very heterogeneous. Changes in aerosol emissions over between these two time periods leads to increases in heat wave frequency in some places, decreases in other places. And these shifts in the aerosol signal are also very co-located with where people are located, as we might have anticipated based on that population and aerosol optical depth map I showed you at the beginning. And so what we see is that when we think about now from the heat wave hazard to the exposure, or essentially how many people are exposed to the effect of heat waves, what we find is that aerosols have an outsized influence. So here I'm showing you just the aerosol component of the global land average number of heat wave days per year through time. And so you can see that over the historical period in the fuchsia line, I'm showing you just the hazard. So this is just the raw global land averaged value. You can see that in fuchsia over the historical period, the aerosols have been suppressing this heat wave hazard. And then going into the future, as if aerosols decline as they are expected to in the scenario used in these runs, the heat wave hazard will actually start accelerating as a result of those aerosol emission reductions. But then in purple, I'm showing you the exposure, so the population weighted heat wave frequency. And you can see that the aerosol signal is substantially amplified in exposure relative to hazard because of how co-located those aerosols are and the aerosol influence is with where people are. And so if we take this now and translate this into how aerosols influence heat wave exposure for each degree of warming relative to the way that greenhouse gases influence exposure for each degree of warming, what we see is that aerosols have a much larger sort of effectiveness at driving heat wave exposure, but it changes through time. So what I'm showing you here is now the global land average heat wave exposure per unit of global mean temperature change driven by the aerosol signal in purple versus the greenhouse gas signal in green. And this is evolving through time. And what you can see is that right around present day, we happen to be in a spatial distribution of aerosol emissions that is extremely good at offsetting the heat wave exposure from greenhouse gases. It's about 2 to 3 times better at reducing heat wave exposure than the greenhouse gas effect is at driving heat wave exposure. However, that effectiveness is projected to decline in the future as aerosol patterns change. And so what this means is that if we were to scale our expectations of heat wave exposure and heat wave risk based on global mean temperature, we would likely be misattributing how this risk is going to change in a world where aerosols and greenhouse gases are both evolving rapidly. And lastly, I'll share an example from the impact modeling world that really highlights ways in which we need to make sure that we are thinking about the aerosol pathways for impact on different societal systems. And here I'll use the example of crop yields. And this is from a project that has just concluded with a group of collaborators at Stanford, where we took a set of Earth system model simulations designed to isolate the effect of the location of aerosol emissions on physical system and human system outcomes. So we took an identical amount of aerosol emissions, roughly equivalent to what China was emitting in the year 2000, and simulated the effect of those emissions if emitted from each of these 8 regions shown on this map. And then with collaborators, we process the outputs of those Earth system model data sets through damage functions for infant mortality, crop yield, economic productivity, so that we could map essentially how effective aerosol emissions from different regions were at driving these different societal impacts. And I'll show one quick example from the crop yield analysis that we did that really highlights the importance of aerosol aware impact damage functions. So here what I'm showing you is the impact of aerosols from each of those 8 regions on total crop yields. So the thick columns are the total global change in crop yields driven by imposing those identical aerosol emissions in each of the 8 regions. And then the thin lines are showing the contribution to that total from each of the environmental parameters that go into that crop yield damage function. So aerosol optical depth, precipitation, and temperature. And I just want to draw your attention to the example of the effect of US aerosol emissions on crop yields. And you can see that aerosol optical depth in the light blue, the damages to crop yields from the increase in aerosol optical depth entirely counteract the benefits to crop yields from the cooling that the aerosols contribute, resulting in a change in sign of the total crop impact. So taking the crop yields from a net increase to a decrease. And so if we think about how we would construct a crop yield damage function, if we were thinking only about greenhouse gas driven impacts, we might think about precipitation, temperature, maybe CO2 fertilization. We probably would not be thinking about the role of aerosol optical depth. But what this sort of decomposition shows is that neglecting that aerosol component would give us a fundamentally different understanding of the role of sort of total anthropogenic emission changes on these societally important factors. So I hopefully have painted a picture for you that demonstrates the importance of these regional aerosol emission changes and the uniqueness of their influence on the climate system and the ways in which those can impact these societal impact factors and these climate risks in a way that is very distinct from that of greenhouse gases, and that is also likely neglected by the way that we've constructed this climate risk assessment framework. So now that I've spent all of this time complaining, I would be remiss not to try to provide some way forward, a way that we can try to address this issue as we think about assessing environmental risk going forward. And I think there's a role for sort of everybody in the pipeline of information from initial generation of the scenarios that go into the Earth system models, all the way to the people actually making adaptation and resilience decisions. So I think at the level of integrated assessment modeling, there's a real opportunity here, and this work demonstrates that the uncertainty from aerosols is likely to play a large enough role in the uncertainty in climate risk going forward that it's worth investing in ensuring that we have sufficient scenario diversity in our projections of the future. And so I think that's a conversation happening right now in the context of CMIP7. And I think there's a real opportunity here to make sure that we're investing the time in capturing a robust range of potential outcomes on the aerosol emissions side. And I think the importance of the aerosol piece also encourages sort of greater critical analysis of the assumptions that are driving the emissions of aerosols in these future scenarios to help ensure that we are actually capturing plausible future outcomes, not just at the global scale, but also at the regional scale. I think for the Earth system modeling and aerosol climate research community that I sit in, the importance of these aerosol trajectories and aerosol effects for really important societal outcomes hopefully sort of reinvigorates the need to continue improving aerosol representation and aerosol biases in these Earth system models, which has been a continued point of frustration for model developers. But I think the demonstrated societal implications indicate that this is a worthwhile place of continued investment. It also suggests that it's worth investing the computational and personnel effort into Earth system modeling efforts that are dedicated towards the aerosol signal. And I'll just share one example of that I'm currently involved in, the Regional Aerosol Model Under Comparison project. This is a project that's underway right now, expected to produce data publicly available in summer of this year, that's really designed to sample that uncertainty by 2050 that I showed in the previous slide. So we're designing these simulations to sample what that uncertainty by 2050 in aerosol emissions means for near-term climate risks. So this is a set of couple transient simulations through 2050, where we've taken the SSP 37 high emissions scenario as our baseline and perturbed the aerosol emissions globally and then in individual regions down to the SSP 126 low emissions baseline, which is that lowest line there. And so this really lets us isolate the role of this aerosol uncertainty in near-term uh, climate risk uncertainty. And I'll quickly highlight one of the preliminary results that we're seeing from this that highlights the benefit. Here I'm showing you some of the results that we have initially for fire danger. So this is showing the number of high fire danger days, so days with a fire weather index above 30 at mid-century relative to a historical baseline. And on the left is this SSP 37 sort of high emission scenario. And on the right is SSP 126, a low emission scenario. And one of the things that immediately jumped out to me looking at this is that the total global average number of high fire danger days, as well as their regional distribution, is extremely similar between a world in which we take very aggressive emissions mitigation action and a world in which we take essentially no emissions mitigation action. And what the ROMEP data is allowing us to do now is decompose the effect of that aerosol uncertainty in contributing to the difference between these two potential future trajectories. And one of the things that we're seeing is that the effect of the aerosol emission reductions between the high emission and the low emission scenarios, which is what I'm showing on the bottom left, essentially entirely offsets the benefits to fire danger of the greenhouse gas emission mitigation between those two scenarios. So the choices that are made about aerosol emissions over the next few decades are going to be very key to the way that these societal risks manifest. So I'll close by highlighting some of the ways that I think all of the data that's being generated by the Earth system modeling community can be integrated by sort of downstream users to better incorporate this aerosol component of climate risk. I think people who are doing impact research or providing climate services to decision makers really need to be thinking about making sure that their translational tools, their emulators, their simple climate models, their regional climate models, their downscaling tools are aerosol aware and capable of capturing these effects that I showed earlier. Ensuring the same for their impact models, the damage functions that we're using, ensuring that they're capturing the unique pathways through which aerosols may impact these societally important processes like crop yields or economic productivity. And then I think among policymakers and stakeholders, there's a need to break this sort of chicken and egg cycle where aerosols have not been seen as important because the work has not been done to demonstrate that they are important, and therefore the aerosol aware risk assessment information has not been demanded. So I think there's a need for increased sort of communication and awareness raising among those communities, and ensuring that any findings from sort of new information that's generated is integrated into policy discussions. And I think a key part of this will be ensuring that clean air regulation and efforts happening there are sort of coupled with the way that we're thinking about environmental and extreme weather risk going forward, because this clearly shows that choices that are made around clean air regulation, which in turn influence aerosol emissions, will have a major impact on climate risk. And then lastly, I think there's a major role for funders, universities, scientific societies to help convene the very interdisciplinary groups of people that are going to be necessary to address this problem. So with that, I will say thank you, and I really look forward to getting feedback, questions, and comments on all of this. Thanks.
All right, thank you, Geeta.